And as you know, that these are the material mainly preferred for the spring material. And the terminology used in the helical springs that you have seen that as it is made of a wire by coiling process, either hot coiling or the cold coiling process. Now the wire diameter D is very important. So small d, the wire diameter of the spring, and as you know, the di and d naught is the inside and outside diameter of the coil. Inside diameter means over the cylinder over which the coiling has been taking place. That cylinder diameter is basically inside diameter of the coil. And mean coil diameter is the di, mean of di and d naught. Now next is the spring index. That has, you have to choose the ratio of the mean coil diameter to the wire diameter, and its value varying from the 3 to 12, and more preferred value is 6 to 10. Why it should not be less than 3 and why it should be greater than 12, that I have already explained in the last class. I have also discussed about the different terminology related to the helical compression spring, that is the solid length, compressed length, and the free length. So that terminology I have already explained. Now here two things. One is the total number of coil and another is the number of active coil. Total number of coil and number of active coil may not be same because of the end condition. It depends on the end condition. Few more terminology is the pitch of the coil and the stiffness. So that, as you know, the stiffness is very important property. So stiffness of the spring, or the which is also known as spring constant or rate of spring or the gradient of the spring. We have explained here one definition, that the stiffness of the spring when it is acting, force is acting in axial direction. So that that stiffness K is known as the axial spring force divided by the axial deflection of the spring. So that particular thing we will use in our helical compression spring. So we have also explained the spring when it is connected in series, the equivalent stiffness K series. It is related with the relation 1 by K series equal to 1 by K1 plus 1 by K2 plus 1 by K3. But if the spring is connected parallel, then the equivalent spring stiffness, that in K parallel equals to K1 plus K2 plus K3. Now end style. So end style is very important, and based on that, during the uh, this one, you see the end style is the plane end. If the spring has simple end, there is no grinding at the end, no grinding operation. The number of active coil equals to total number of coil. But it is the square ground. If it is a plain ground. So if it is a plain ground, then number of active coil equals to total number of coil minus one less, because it has been grounded 50% this side, 50% this side. Two more is there, square ends. If it is a square end, then number of active coil equals to total number of coil minus 2, means 2 less. Similarly, squared ground also, the number of active coil equals to total number of coil minus 2, or in other words, you can say the total number of coil equals to number of active coil plus 2. So this relation you have to. Now, in order to do the design analysis of closely coiled helical spring means your helix angle is very small. You have to formulate two equation. One is to load stress equation, another is the load deflection equation. So very fast step, you have to know the how much load is acting. Then due to that load, what could be the internal effect. So first you have to see the external load that I have already explained. The P load is acting along the axis of the coil. So here this one is called the axis of the coil. So in terminology, this is called the axis of the coil. Now P is acting. Now equivalent for, but my interest is internal effect at the cross section. Internal effect at the cross section here. So that means what could be the equivalent load couple diagram at the center of the centroid of this wire cross section. So last class I will already explain. You can apply the P force red color, P force black color equal and opposite. It will neutralize each other. So that is where this loading pattern is equivalent to this loading pattern. Now this black creates a couple of anti-clockwise direction, and its magnitude of the couple equal to P into D by 2, but couple vector direction you can see in the side view. So this is your couple vector direction. So this is the couple vector direction M, and it has a two component M cos lambda and m sin lambda, and from here it is clear as lambda value is very less. So m cos lambda, that means m equal to p into d by 2 cos lambda towards 1, that is how you can approximate it, that this particular component, that means the component which is the component of the moment vector which is along the axis of the wire. This red white color, this is axis of the wire. It's not the axis of the coil. This is called the axis of the coil, and this one is called the axis of the wire. So any couple acting along the axis of the wire, that will create the torsional moment or the twist, and corresponding to that internal effect will be the torsional shear stress. So that is your P into D by 2 into cos lambda, but cos lambda is very small quantity. We will approximate this is equal to cos lambda equal to not towards end. Sorry, as the lambda is very small quantity, so cos lambda value is approximately 1. So ultimately it equal to P into D by 2. Whereas the sine lambda, that which will create the bending effect, this particular component, that is your P into D by 2 into sine lambda, as the lambda value is less towards 0, say, then sine lambda is towards 0, that means this value is negligibly small. That will create the bending, but we'll neglect this one to approximate because its value is very small in compared to the torsional effect. Now just see, as you have seen, this is your load diagram. Load diagram, you have seen that the two types of load is equivalent torque, equivalent load torque diagram says in this particular cross section there is a resisting couple T and the resisting shear force, because this P will create direct shear of the cross section. That means the shear stress will be resisting. That means the resisting force. So shear stress will be distributed upward direction. Its direction will be upward. That means shear resisting force will be upward direction. Similarly, torsional shear stress, that means which will create the resisting couple, that will be in a clockwise direction, that I have shown here. So this is the external things. This P is the external load passing through the CG of the cross section, and here M, that means the upper after approximation, it's not M. Let us this one now T will be P into D by 2, that is external. So resisting one will be this one. So if it is so, now you individually treat these two things. So this is my T, that T equal to P into D by 2. This is the resisting couple, and because of that, that means it will create the torsion. Because of that, over the cross section, torsional shear stress will induce. And as you know, the torsional shear stress formula, that tau s equal to T into rho by J, where T equals to, from here you can get the P into D by 2, and rho equals to, at the extreme fiber it will be D by 2, and J, the polar model, moment of inertia, is equal to pi by 32 into D to the power 4, and from here you will get 8PD divided by pi dq. Distribution, at the end it is the maximum. It tau s is directly proportional to your rho, directly proportional to rho. When rho equals to 0, this value will be 0. When rho equals to D by 2, it will be maximum. And this is the stress distribution that you know from your shaft class, torsion of a shaft. Now another thing is remain, that is the resisting force will create the direct shear of the over the cross section. So what could be its magnitude, or the because of the force P, direct shear should be uniformly distributed. Why uniformly distribution? Because here we have seen that P is passing through the centroid of the cross section. Whenever your force is passing through the centroid of the cross section, it will create if it is axial or if it may be direct shear, the formula that may uniform stress distribution criteria is valid. Uniform stress distribution criteria says when the force passes through the centroid of the cross section, your stress will distribute uniformly over the cross section. And here, because of the P, the stress is shear stress, it is shear off. So that is why the shear stress distribution is uniform. Now you just add vectorically these two stress. Individually you can find out the internal effect. So internal effect due to T you found out, internal effect due to P you found out. That means this one and this one, and you add it vectorically. But here you see the cross section, both are lying in the same plane. If you can attach the axis properly, as you know the axis you have attached in case of a shaft, same you can attach the axis. Let us say this is y axis and this is the z axis. Here also this is the y axis and it will be the z axis, say. Then both are lying in the same plane and acting along the same direction, that is the z. So vector addition means here simply algebraic addition. If you add it, now just see the this 50% it is same as same direction, but the remaining right hand side, the direction here it is the negative direction, here is the positive direction. And because of that you just see as there is a zero, but here is a certain magnitude in this case. That means when you add this one, so here after resultant there will, at center portion there will be no zero because of this one. It will zero is shifted towards right because this particular negative and positive neutralize in between somewhere here. So this is your stress distribution, and from here it is clear that which particular surface will be highly stressed. For this particular spring, you just see if you cut it, you can easily call this is the inner surface because it is more closer to your coil axis. It's more closer to the coil axis. It is the inner surface of the coil of the wire, and this is the outer surface. This is the outer surface. Now from here it is clear inner surface is subjected to maximum stress always. Inner surface of the, remember this one, inner surface, inner outermost surface, that the inner side, but the outer here the extreme point. So this particular innermost fiber is subjected of the your say in this particular coil is subjected to maximum stress. So that maximum stress, how you find out? You know the tau d equal to simply P by A. It is direct shear stress. So remember, this is the direct shear stress. force is acting tangent to the cross section, and that is why it is called shear stress, and it is called direct shear stress, and that is equal to P divided by area, P divided by pi by 4 d square. That means 4P by pi d square. Now add these two. Now, very important thing is you add it. I like to show you some equation first that I have explained this one. I have already explained this one. Now you add it. The two traces add directly because it is lying in the same plane and same direction. And the maximum shear stress, you can take a common 8pd by pi d cube in this particular equation. You will get 8pd by pi d cube under bracket 1 plus 0.5 divided by c. What is c here? C equals to, as you know, the capital D by small d. So this particular simple derivation you can do it. If you take common this one, then you will get denominator capital D by small d, and that I am writing as a spring index C. Now what is nomenclature has been mentioned here. It is not mandatory to write in a case form, but it is mentioned it is the shear stress correction factor, something like that. But you remember this one, 8pd by pi d cube into 1 plus 0.5 by c. But question is the formula I have used here, tau, the torsional shear stress. If you see the assumption before derivation, the torsional formula of the circular shaft, tau by rho equal to T by J. This particular torsion formula is valid when your cross section is circular, that is complying here, but at the same time your shaft should be straight. So tau by rho equal to T by J formula is valid when your shaft or that particular element or machine, that member, structural member should straight, initially should straight. But in this case, though I have used this particular formula, but it is not straight. You see, the coil is like this. That means if you take the wire is bent wire, it is not a straight wire. As it is not straight wire, because of this curvature, stress value will be much higher than the whatever stress you are calculating by straight shaft formula. So that is why whatever you are calculating, that will give the wrong prediction because of the curvature effect. So I like to skip more detailed analysis of the curvature effect, but the curvature, due to the curvature effect, what could be the correction on this particular shear stress that has been first experimented by the world in the 1929 AM world. First they determined that what could be the correction factor on that particular shear stress which is derived from the straight shaft, uh, so that we can use that formula by multiplying some correction factor. So the effect of curvature of the wire as it forms the coil should be considered. And there is an increase in intensity of the torsional shear stress in the inner fiber. Inner fiber means here, inner fiber means this one, inner fiber, because of the curvature of the coil. And in order to include both the effect of direct shear effect means direct shear, already we have calculated direct shear, as well as the effect of the wear curvature, that means this bend. The wear curvature means this curvature. Wear curvature on the torsional shear stress, a stress factor has been determined by AM World, which may be used to determine the maximum shear stress in the inner fiber of the wire cross section, and this stress factor is known as World factor, and it is very popular World factor for the helical compression, helical spring, or closely coiled helical spring. That world factor is that a world has been carried out experiment, and also by geometric relation used and experiment found in the year 1929, and he has also published the paper on that, and he has dedicatedly written on book also, that's on a mechanical spring, and he has proposed this particular formula. And here both the effect has been considered, both your direct shear effect as well as the curvature effect on the torsional shear stress, and formula becomes now simple: tau equal to kw into 8pd divided by pi d cube, where kw equal to 4c minus 1 divided by 4c minus 4 plus 0.615 by d. So what you can do, that formula you have derived this one, 8pd by pi d cube, under bracket it was 1 plus 0.1 plus 0.5 by c. That will be the wrong one, and instead of that, inside bracket the 8pd by pi d cube remains same. Under bracket will be that kw will be, instead of 1 plus 0.5 by c, it will be 4c minus 1 divided by 4c minus 4 plus 0.615 by c. So he has written one book, you can see one book to show the that experimentation and analytical derivation of this particular formula. Now it is well established formula, worldwide use this particular formula for initial design of the closely coiled helical compression spring. And you can expect such type of objective question on MCQ type of question, where they will ask world factor equal to many relationship. They will number A, number B, number C, a different relationship will be show you by varying certain 4c plus 1, like that way some MCQ type of question you can expect. But you remember the formula is 4c minus 1 divided by 4c minus 4 plus 0.615 by c, where c equal to spring index capital D by small d, and it varies from 3 to 12. And the formula we like to use this particular tau formula. So that this one is the load stress equation. So load stress equation is over. P is the load and the tau the total shear stress acting at the inner fiber. Now is the load deflection equation. Now deflection equation, as you know, the deflection you can calculate by the principle of strain energy, or the using the Castigliano's theorem. So that we like to use here. So deflection equation in closely coiled helical spring, we have assumed that the direct shear contribute negligibly small to the deflection. So torsion formula we like to use where, and again here we are also doing approximately, because the torsion formula T by J equal to G theta by L is applicable for the straight member. But here it is the coil or curvature is there. We are neglecting that particular curvature effect as well as the direct shear force effect. And what we can find out that the formula, torsion formula T by J equal to G theta by L, where theta equal to TL by GJ. Mallodi,
হ্যাঁ স্যার।
শোনা যাচ্ছে?
হ্যাঁ।
Now, where t equals to, as you know, the we already approximated p into d by 2, j equal to pi d to the power 4 by 32. What is L? L is the length of the spring. Now, what could be the length of the spring? Length of the spring, you can also do experimentation if you are unable to find out. Length of the spring means you take a spring from your pen, and the two end of the spring you just pull it. Whatever force you have, using that particular force you pull it. What happens, Mallode? If you pull it by two end of your spring which is in your inside of your pen,
it elongates.
and ultimately what you will get after elongation, what could be the then you will get only one straight where? If you pull it with your maximum force you have, ultimately what you will get?
It depends on the spring actually.
Your pen, the spring used in your pen.
আচ্ছা।
Wire, sir. Straight wire.
Where? So that length of the wire you measure it, that is L. Take a spring from your pen, take it out, at the two end, you can pull it with your maximum force that you can apply, and ultimately within few seconds you will get a wear. You convert the spring into a wear and measure the length, that is L. So that means one complete rotation of the coil approximately equal to pi into d, and you multiply by the number of coil, then it will be pi dn. Clear? L equals to pi dn. Pi d is the one coil length, then multiply by number of coil. But here n is the number of active coil. Now what could be the strain energy due to this torsional load? Equal to, as you know, the strain energy U equal to half into T into theta. Now put the value of the all the your uh, T and theta expression. T is this one, theta is this one. Ultimately you will get T square L by twice Gj. Now what is T? T equal to PD by 2. Put here PD by 2. What is J? J equal to pi d to the power 432. You just put it. After putting, you will get U equal to 4 into P square d cube n divided by G d to the power 4. Now deflection due to the torsional loading can be calculated by Castix-Liano's theorem, which says that the deflection along the direction of the force P equals to the del U del P. Now differentiate the strain energy with partial differentiation of this strain energy with respect to P, then you can easily get the P, it becomes twice P, that means 8P dq n by G due to the power 4. So this is your deflection equation, and stiffness equation, as you know, P divided by the delta, deflection equal to 8P dq by n G2 to the power 4, that you put it here, P divided by 8P dq n divided by G to the power 4, ultimately you will get K equal to G into D to the power 4 by 8 dq n. From here, it is clear your stiffness is directly proportional to 1 by n number of active coil, because here you can say the K, if for example that I have mentioned in the last class, you take your spring from your pen. So this is your spring of your pen. Now its stiffness is say K. Now you can say number of coil here is say N. Now make it half. You can make it half. That means once you make it half, that means each one, this one will be your spring size. This is one, another will be similarly here. Now what will be the stiffness? This is say K1. This is stiffness of the spring, say K1. Now as both are, and the number of coil becomes here N by 2. Number of coil is say N1. Number of coil is here N1. So N1 equals to, in this case, N by 2. As both having the same material, same wire diameter. So you can easily say that your K, this K equals to is this one. Now this K1 equals to, you can write the K1 equals to your G is remain same, material is same, D is same, so D to the 4 is same. Now 8 will be remain same, DQ will be remain same. Only thing N becomes now K1, N becomes N1. As N becomes N1, from here it is clear that G due to the power 4, N again N equal to how much? N1 equal to N by 2. N1 equal to N by 2. So that means K1 equals to twice 2, it will be above 2 into K, because G due to the power 8 dq n equal to K. So K1 equal to twice K. So from this particular formula you can easily prove, so K1 equals to double of K. When you make the spring half, your stiffness become double, because stiffness is inversely proportional to number of coil, or K is proportional to 1 by n, where n equal to n by 2, then K becomes double. So now we like to do some example. We like to show you how to analyze or how to find out the your dimension of the spring for a particular application. Now in design, first you have to know its objective. So and it should have a sufficient strength to withstand the external load. Spring should have a required load deflection characteristics. This is very important. The spring, many applications, spring have to require the load deflection characteristics. It's not like that arbitrarily it will deflect. So load deflection characteristics is very important in case of a spring because it is applying force, is giving motion to the other components. So opening the valve, opening the some clutch plates. So that is why load deflection characteristics is very important. And spring should not buckle under the external load. You have seen in the automobile that spring is inside there is a mandrel. In case of a bike, you might see spring is over the a particular cylinder so that it will avoid buckling. That particular inside cylindrical thing can take care of that buckling. So if it is there is a tendency of buckling, then you have to have a inside cylindrical things which can be support or it can should not make it buckle. So in design, what you have to find out the wire diameter. Most important thing you have to find out the wire diameter. You have to estimate the wire diameter and you have to select the wire diameter from the standard wire available in the market because you can't do any turning operation to get any diameter. So wire diameter you have to predict or you have to estimate from the load stress equation, and you have to find out the you have to nominate or you have to recommend the standard wire diameter, mean coil diameter or spring index. Once you know the wire diameter and once you select the spring index that you have to select, spring index you have to select, you can easily find out the mean coil diameter. Now, number of active coils that you have to find out, and that is possible on because you see the stress equation. There is a no use of n. If you can recollect your equation, you just see here. So in this particular equation, you just see it is independent of n. Tau is independent of n. There is no n here. So whenever you like to calculate the number of active coil, you have to use the load deflection equation because the load deflection equation, deflection is the function of n. Deflection is function of n, and that is why load deflection equation is required. Other than that, other parameter is the angle of helix that you have to select, pitch of the coil you can find out. Afterward, once you get other thing, it is related with the n, number of coils, and the free length and other things. And you have to assume that after compression, what could be the minimum gap should have to be maintained, and stiffness of the spring you can easily derive. But practical limitation is there. Whenever you like to design anything, you have to see a particular machine component is surrounded by the other machine component. So that means there is space limitation. So space limitation from the outside and the inside diameter of the coil, you have to keep in mind when you like to recommend any dimensions. Not only spring, for other machine component also, space limitation is also important. So basic parameter you have to find out, that is the wire diameter that you can get from the load stress equation. And spring index you have to assume, you can easily find out the relationship C equals spring index equal to mean coil diameter by the wire diameter. Next you have to find out the number of active coil, and for that load deflection equation is important. So you have to use the load deflection equation. So now steps, as you know, that you have to know that it's function of the spring, then find out the load acting on that, select the suitable material, then the mode of failure, either it is the shear failure in this case, find out the geometric dimension based on that particular failure, and then you check the dimension from the assembly point of view, standard manufacturing, means the standard material, standard wire dimension point of view, check and recommend the dimension, that means the wire diameter. So these are the steps. So first step, you have to know that your functions, whether it is used to absorb shock and vibration or it is used to apply the force, or that you have to first identify. Then you have to find out the load estimation, that engineering mechanics. Estimate the maximum spring force. So it may not be given in your problem directly. You have to find out how much is the force acting on each spring and what is the line of action of that external force on the particular spring. That finding out that is very important. So load may not be given directly. You have to find out by solving your engineering mechanics problem to find out the spring force. That means you have to find out the magnitude, direction, and the line of action of the force. And you have to know the required deflection and the required stiffness property. Now load is, as you know that from your fourth semester machine design class, load may be time varying, or it may be its magnitude, direction, or both, or magnitude, direction, both are not varying with respect to time, then it is called the static load. If it is any of these two is varying, then it is called the cyclic load. And impact load is means when the application of load is basically momentarily, so that time there will be impact effect. So we start with the static load only, because always we have to solve when the simple problem relatively, when the load acting on the spring is static in nature, then you fine tune it for your cyclic loading or impact loading. So now we like to start the design under the static load. What are the steps you have to follow? Once you do the load analysis, you have to select the material based on the load acting on that, in which environment it is working, and what are the other criteria, like the fatigue is you are vulnerable or not, and depending on that you have to select the material. And always in design, it is a iterative process. You start with a low cost material, easily available low cost material. Always you start with the always, most of the time, if you don't have any prior experience, then try to start with the relatively easily available material and the low cost material, so that your product cost will be less. But provided if you don't have any prior experience, and you have to iterate. If it is not serve your purpose, go for the higher strength, high strength material. So that is why it is iterative process, and you have to write your own code, or you can use any software like Excel to do this sort of iterative type of iterative work in machine design. Next, once you select the material and material property you will get from the data book, then you choose the suitable factor of safety. Now, factor of safety in the design of spring is chosen as a 1.5 or less. So my question is, why the factor of safety is relatively less, 1.5 or less? In case of a shaft, another case it is 2.5, 3, like that. But here we have chosen it 1.5 or less. The reason is, for choosing the relatively low factor of safety, the most of the applications, spring operates in a well-defined deflection. Therefore, the forces acting on the spring and the corresponding stresses can precisely calculate it. So calculation uncertainty is relatively less. Uncertainty is always there, but it is less in respect of other where stress concentration is exists. So it is not necessary to take higher factor of safety to account for the uncertainty in external force calculation. Another reason is, in case of a helical compression spring, an overload will simply close up the gap between the coil without dangerous increase in the deflection of the stress, and that is why there is a less chance of accident, and no need to take the more factor of safety to take care of the more uncertainty, because uncertainty is less, because if any overload will come, it is simply close up the gap between the coils, and it will not create any excessive deflection or the stress. In case of a helical extension spring, if excessive load will come, then that overload will stops. Overload stops are provided. In case of a your extension spring, there is a mechanical means which will stop the overload, provide the overload prevention mechanism is there to prevent excessive deflection and the stress, and that is why relatively lower factor of safety has been chosen in case of a spring design. Now, what you have to design? So, very first step in design analysis, you have to choose the suitable spring index. So, preferably its value is for helical, closely coiled helical compression spring. C value, the spring index value is choose 6 to 10. Some cases you can move up to 3 and there up to 12, but preferably within the 6 to 10. Once you know the C, then you can easily find out the world factor, because world factor you already know 4C minus 1 divided by 4C minus 4 plus 0.615 by C. It is a function of C. So you can easily find out the world factor. Then you can find out the stress where the wire diameter is unknown. From the load stress equation, you can find out the wire diameter. Once you know the wire diameter and the C, you know the C equal to capital D by small d. C is known to you, small d is known to you. You can easily find out the mean coil diameter capital D. Next, you have to calculate the number of active coil, and that for that load deflection equation you have to use. And other derived quantity you can easily find out, because assume the many things like gap between the two successive coil when it is in compressed condition. Now let one more thing I like to show, that helical compression spring that is too long compared to the mean coil diameter then act as a flexible column and may buckle at a comparatively low axial force. The spring should preferably design as a buckle free, and the compression spring which cannot be designed buckle free and must be guided on a sleeve or an arbor which is used in your automobile or your what is called that your bike, that you have seen, that I like to show you once again. See, in this bike inside there is a arbor. So in order to avoid buckling, there is a arbor. Here also you just see same thing. It may dual role may play, but this thing is there inside, because there is a tendency of buckling this particular spring. And the thumb rule for provision of guide is, if free length divided by mean coil diameter is less than 2.6, no need to use the guide, that means sleeve or arbor. But free length divided by the mean coil diameter is greater than 2.6, then you have to provide the guide. But provision of guide results in the friction between the spring and guide, and this may damage the spring in long run. That you have seen, that spring will in contact with the arbor, and there will be a rubbing, or there will be, because of the friction, it may damage the spring surface. So this I have already explained. Now I like to show this numerical problem. So you can open your copy to solve this one. Otherwise, very simple problem, you just see this. The problem statement says it is a design analysis problem. So a helical compression spring, obviously closely coiled helical compression spring made of a circular wire, is subjected to an axial force which varies from 2.5 kilonewton to 3.5 kilonewton. Over this range of force, the deflection of the spring should be approximately 5 millimeter. The spring index, that means capital C, can be assumed as a 5. Here it is mentioned as a 5, so it is within the range of 3 to 12, so it is okay. The spring has square and ground end. That basically tell you total number of coil equal to number of active coils plus 2. So that will be the information we will get from this particular statement. Now, spring is made of patented and the cold drawn steel wire with the ultimate tensile strength of 1050 MPa, and modulus of rigidity is 81370 MPa. The permissible shear stress of the spring material should be taken as 50% of its ultimate tensile strength that has been given. Ultimate tensile is given, 50% of that will be the permissible shear stress. That relation has been provided here. So no need to assume factor of safety because already it has been mentioned what could be your permissible shear stress. Now you have to estimate that wire diameter. So that is the most important thing. You have to recommend the wire diameter, then the mean coil diameter, number of active coil, total number of coil, then solid length of the spring, free length of the spring, required spring rate, and the actual spring rate. Now just see the important thing here. Most important thing in this particular problem is this one and this one. Now, can anyone tell how much is the maximum load is acting on maximum axial load is acting on the helical compression spring in this case? It has been mentioned axial force varies from 2.5 kilonewton to 3.5 kilonewton. That means what could be the maximum axial force? Maximum force. Aman Agarwal. Amanji.
Yes, sir.
Maximum force.
3.5 kilometers, sir.
जोर से बोलो. अमन जी जोर से बोलो.
So 3.5.
3.5 kg.
So
Gram.
kilonewtons.
Huh?
Sir, 3.5 kilonewtons, sir.
Okay, 3.5 kilonewton. Now material has been mentioned, cold drawn patented steel, then SUT is given as your 1050, then G is given as this value, then permissible shear stress of the spring material is 50% of SYT, that means 525 Newton. Now first you have to calculate the wire diameter, and in order to calculate wire diameter, you have to use the wall factor. So wall factor is Kw. Kw is given as 4C minus 1 divided by 4C minus 4 plus 0.615 by C, and put, as you know, the C value, spring index value already it is mentioned. You choose the C equal to 5, put the value, you will get Kw. Now as you know the Kw, then you know the tau equation, tau equal to Kw into 8P. Here that formula, you know that from here d by small d is written as a C in this particular form. Any form you can write, because the form originally I have shown here is the 8PD by this, so this you can easily write Kw into this 8P pi d square, pi into, instead of dq, d square. Now 1d or capital D by capital D equal to C. Capital D by small d equal to C. Now here it will be the pi d small d square. So this formula has been written in the fashion of C, in terms of C and small d. So that is made, and put all the value. This should be less than this, the permissible tau is this one, and this should be less than the formula is less than, so the induced stress should be less than the permissible 525. From here you will get D should be greater than this millimeter, 10.5 millimeter. Now I like to show you the data book. So data book, I don't know whether it will be visible or not. Now this is the preferred wire diameter available. You just see here. Now you got the D greater than 0.55. Which D is available here from this particular table? D is greater than this millimeter. This is greater than this. That means 10.55 calculated value. Now look in this particular table and move here. Higher than 10.55 is the 11, or you can choose 11, 12. That is your choice. So better to choose the 11 because of the nearest to the 10.55. So recommended value. So your recommendation, it is your recommendation is D equals to standard diameter 11 millimeter. Clear? So wide diameter is over, then you can easily get the capital D, because capital D equals to the spring index multiplied by small d, that means 55. Now my question is here. So you got this one. In this particular case, you got the wire diameter, you got the mean coil diameter. Now you have to find out the number of active coil. So as I mentioned, in order to find out the number of active coil, you have to use the load deflection equation. So load deflection equation, you already know that its deflection equation is 8 PDQ by N GD to the power 4. From here you can easily get. So 8 PDQ N divided by GD to the power 4 equal to deflection. अंकित कुमार है क्या? अंकित कुमार
Yes, sir.
बोलो द इक्वेशन, डिफ्लेक्शन इक्वेशन बोलो, देख के बोलो डिफ्लेक्शन इक्वेशन.
8p d cube capital N by GD की power 4.
Okay, now deflection. How much is the deflection in this particular problem? So once again, you just tell me deflection equals to 8 p d cube n divided by
Capital G. Okay.
4. Now tell me, you have to find out. Your objective is to find out the n. N you have to find out. That means deflection is given to you. How much is the deflection?
5 millimeter.
5 millimeters. Now you that known G is known to you. How much G?
Capital G. 31,370 Newton millimeter square.
This one, good. It is unit is also correct. Newton millimeter square. Here 5 Newton. So dimensional compatibility is okay. Now what is D? Small d. How much value?
11 millimeter.
11. Capital D.
55.
55. Now P. P value.
Very
Ankit Kumar, P value.
2.5 Newton to 3.5 Newton. So variation 1 kilonewton का है. So 1 kilonewton variation. Hello.
What? Hello.
Yes, sir. P is equal to 1 kilonewton.
P should be, P is the 1 kilonewton. Why?
So एक deflection sir वो 3500 3.5
Because it has been mentioned when axial force is varying from 2.5 kilonewton to 3.5 kilonewton, because of this variation of the force, there will be a deflection 5 millimeter.
Yes sir.
Because over this range of force, deflection of the spring is 5 millimeter. That means when you apply when you change force or when you increase the force 2.5 kilonewton to 3.5 kilonewton, and that time your deflection has been increased by 5 millimeter. That means 5 millimeter deflection is because of the increase of the force. That means increase of the force how much? 3.5 minus 1 2.5, that means 1 kilonewton. So here the P is the force which is responsible for the delta, and that is why P value here will be 1 kilonewton. Clear?
Yes sir.
So that means 3500 minus 2500, and from here you are getting n equals to 4.48, but n should not be in fraction. It is the number of active coil, that is why you just round it up with a higher value, that means 5 number of coils, and then your total as your end is the square and ground end, number of active coil is 2, number of inactive coil is 2, and that is the total number of coil equal to number of active coil plus 2, that is 5 plus 2 equal to 7. Next is the calculation of the different solid length, free length. So you can easily the solid length. So solid length you already know that is the diameter multiplied by total number of coil. That means wire diameter. Wire diameter is 11 multiplied by total number of coil means 7. 77 is your solid length. Other length, how will find out? You have to assume. You have to assume the gap after the maximum load is acting. So you just assume this is the 0.5 millimeter. Being a designer, you have to assume based on your requirement. Clear?
Sir, how to put that assumption?
You have to assume. Designer has to assume, no?
Means you can select 0.6 also, 0.6, 0.7 also.
You are the designer. You have to assume. What basis you assume? It depends on the problem. I'm repeatedly telling you. You from your mind, you just remove all these things. Design means you are the designer. You have to take decision. What will be the basis for that? What will be the problem? Accordingly, you have to choose. So there is no hard and fast rule. There are some guidelines. There are some standard that you have to follow. Only Bhandari book will not serve your purpose. You have to open your mind. You have to go through the company's catalog. You have to go through the data book, and it is open book kind of thing. Design is the open book problem.
Yes, sir.
So whether you will take 0.5, 0.6, it is your choice. If you take more, there is a more tendency of buckling. If you take less, then there is if any overload will come, then it will quit fast.
Okay, sir.
And how much you can maintain 0.5 millimeter or 0.1 millimeter, that is your choice. It is very difficult to maintain 0.1 millimeter. No, there is a surface roughness, any other issues. There manufacturing error is there. So all this practical sense you should have to choose a particular gap. It should not be the 0.1. How will 0.1 is it's impractical, because then wire may not be completely smooth straight. You know the manufacturing process, a lot of limitation.
Yes, sir.
So that is why you have to follow the data book. In this case, they have chosen 0.5. You can choose 0.6, 0.45, whatever you like.
Okay, sir.
You have to justify whenever you like to solve your real life problem, not in semester exam, but you have to justify whenever you choose anything. You have to justify either you justify that is recommended in this data book, or it is because of this, like that. You have to write some justification under bracket. So that way you just find out. And here another thing, the actual deflection of the spring under the maximum load, how much. Once you know all the number of coil, you can find out actual deflection due to the total load. This one, that has to be added here. So it is because of the total load, because that has been mentioned problem 2.5 to 3.5. If it will increase, then 5 millimeter is the extra deflection. But how much the actual it has been happened, because you have already applied 0 to 2.5. How much will be that one? So that is why better to find out the 3.5 directly. When 3.5 is applying, how much is the, otherwise what you have to do, if it is a 2.5 kilonewton load, how much is the deflection? That deflection plus 5 will be the this one only, same value will come. So in this way you can find out the free length, because free length is very important, because how much space is required during assembly or how much space is available. So free length is important. So your free length should be such that it should be accommodated. The helical compression spring should be accommodated within the given space. So free length should not exceed that particular given space. If it is exceed, then it will be preloaded or you cannot assemble. So this way you do the calculation, few more problems, solve it. If you have any doubt, just tell me. For my part, it is over. So I will give the assignment problem. So these are the problem already I have taken from the Bhandari's book. One is from the compression spring for the valve opening and closing in IC engine. Another is again, it is the clutch mechanism. So both are you are in this semester you are learning valve mechanism in your IC engine class and the clutch mechanism in your machine design class. Both case spring is required and spring design is the designer's job. So you have to design that these two springs. So you please solve these two problem, and one no need to submit anything. You just solve this particular problem. An assignment problem I will give you. So any doubt? So these two problems you solve it at your own interest for the gate exam point of view or whatever maybe you like. So you just solve. I think it will take hardly 10 minutes to solve each problem. Okay, any doubt? Otherwise, if you don't have any doubt, then I like to stop. Malladev,
Yes, sir.
attendance ले लो भाई.
हाँ सर निश्चय.